Hi, and welcome back to our next video on the present value of an ordinary annuity. So let's define this term first. So present value of an ordinary annuity is the amount of money invested now to provide a series of equal payments at equal intervals of time. You can say that this is the opposite of the amount of an ordinary annuity because in the amount of an ordinary annuity, you are providing a series of equal payments at equal intervals of time to get a final amount. In the present value of an ordinary annuity, you're trying to figure out how much to invest now so that the bank pays you a series of equal payments at equal intervals of time. So let's look at the formula now. You can see that present value, or PV, is equal to R bracket 1 minus 1 plus I to the power of negative n divided by I, where R is the payment made at the end of each compounding period, n is the number of compounding periods, and I is the interest rate per compounding period. Let's move on to our first example. Just move that over. Oh, look, it's already here. So, John wants to purchase a new car from his friend for $50,000. His friend agreed to give the car to him now, with regular payments made every 3 months until the entire sum was paid off in 2 years, with the first payment made in 3 months. How much would John have to invest now at an interest rate of 6.5% per annum, compounded quarterly, to have the amount for the payment? So first of all, let's write down our formula for present value, which is PV, present value, is equal to R bracket 1 minus 1 plus I, the power of negative n, divided by I. So as yet, we do not know our present value. We're trying to figure out how much John has to invest. But we can figure out our R value. So we know that he has to make payments every 3 months for a period of 2 years, which means he has to make 8 payments in total. 8 payments. So to figure out how much each payment would be, just divide 50,000 divided by 8 payments would be $6,250 per payment. Let me just double check if that's correct. Yep, $6,250 per payment, which means that is the amount that the bank has to pay him every 3 months to compensate for the amount he's paying his friend. So R here would be $6,250 bracket 1 minus 1 plus. Now be careful here because the rules that apply to compound interest and amount of an ordinary annuity do not disappear for present value here. You have to apply the same rules, which means that you have to make the interest rate, which is 0.065 or 6.5%, and divide it by 4 because it is per 3 months, which is a quarter of a year. And since the interest rate is 6.5% per annum, compounded quarterly, you have to divide this number by 4 to get the interest rate per 3 months. And we already established that there were 8 payments, so 8 compounding periods. So to the power of negative 8 divided by I. So if we simplify that, bring out our calculator, we have 0.065 divided by 4 equals that much, plus 1 to the power of don't exactly see that button. I'll just use my calculator out here. So we have 0.065 divided by 4 plus 1. You guys can follow along with your own calculators if you have them too. To the power of negative 8 is equal to 0.879, and subtract that from 1. This gives me 0.120. Divide that number by 0.065 over 4. This gives me 7.44. I won't write this number down because it's a rounded off number, and I've already established before the importance of keeping things as absolute or whole well, as precise values, not rounded off numbers. So in this case I'll round it off, but in the next step I'm going to use the value that I found, or that the calculator gave me. ... So when you multiply this by 6,250, your present value is equal to $46,533.28, or $46,533.28. That is how much John would have to invest. Let's check if our answer is correct. Yes, it is. We have that much. So let's move on to another real-life example. So we all know that there's a new kind of space race now where private industries want to send up tourists to the moon and have them pay bulk sums of money to basically view the moon. So let's say that Mary recently won a lottery and wants to go on a tour around the moon. She's one of those people who's rich and wants to spend money. However, this tour is very expensive, as one would imagine, so the tour company allows tourists to pay monthly installments of $15,000 for 10 years so they can afford the cost. Mary wants to invest her money in an account that has an interest rate of 7.8% per annum, compounded monthly. How much should she invest? Alright, so to go about solving this problem, just switch back to copy this question to the program so we have it at our disposal. Just copying, just put it all on one line. Alright. So again, as always, let's start off by writing our formula for present value. So we have, switch to brush first. Present value is equal to R multiplied by 1 minus 1 plus I to the power of negative n divided by I. So first of all, again, let's look for our givens here. We do not have our present value. We don't know how much Mary has to invest to get the amount she wants. But we do have the R value. We know that she needs $15,000 every month. So our R value here would be $15,000. Let's move on. So we have 1 plus interest rate. Again, it's 7.8% per annum, but it's compounded monthly. So we have to divide this value by 12 to get the interest rate per month. So you have 0.078 divided by 12, leave it as a precise value, to the power of, what would the n value be here? Well, we know that she's doing it for a period of 10 years, and it's also per month, to pay monthly payments of $15,000 for 10 years. So 12 months in 1 year for 10 years would be equal to 120 months in 10 years. So the value we're looking for here is 120 to the power of negative 120 divided by the interest rate, which is again 0.078 over 12. So if I put that in my calculator here, you guys can follow along. We get 0.078 divided by 12 plus 1 is 1.0065 to the power of negative 120 is 0.459, which is a rounded number, obviously. Subtract that from 1 and divide it by 0.078 over 12, which is approximately, again, this is a rounded value, and I am going to use the precise value for my next step, which is approximately 83.14. So if we multiply that by 15,000, we get a value of $1,247,158.80. So that is our present value. That is how much Mary has to invest to afford this spaceship, and that is a whopping amount, as one would expect from a spaceship. So let's check our value with the actual answer, and we are correct. So let's move on to a counterexample. So we saw this example before for our ordinary annuity video. So let me just read it again. So if John got a part-time job at Burger King during each of his summer breaks at high school, at the end of each summer, he deposits $1,500 into an account with an interest rate of 4.5% compounded annually. How much money will he have by the time he graduates if he starts depositing the summer before grade 9 and makes his last deposit the summer before grade 12? And we already established that the answer to this question was $6,417.29. So that is how much he would have by the time he finishes grade 12. So let's continue on with this question. So if John wants to withdraw yearly sums of money to pay for his university education after grade 12 using this amount, how much money would he withdraw each year? So let's go here where the question is. So first, again, let's write down our formulas. And in this case, I think it's good to write down the formula for the amount of an ordinary annuity as well. So let's write that down. We have amount is equal to R 1 plus I to the power of n minus 1. The whole thing divided by I. And we already know that our formula for present value is equal to R bracket 1 minus 1 plus I to the power of negative n. The whole thing divided by I. So the question here is asking us how much money he would withdraw each year. And at this point, most people would stop and say, hey, if the amount at the total end of this formula is $6,417.29 using this formula equals that formula, then that means the R value has to be the same. So they would say that the R value here would be equal to $1,500. And this is a common mistake. It is not correct to establish this because you have to keep in mind that the money has been sitting in a bank and it has matured. So you would not have this value here because this value would have gathered interest. So what you have to do is that you have to take this amount, because this amount here will become your new present value. So you would input your present value here for $6,417.29 because that is what he starts with before grade 12. He has this amount of money when he first starts university, and he's using this amount of money to give out yearly payments. So let's substitute our knowns into the formula. So we already established that this thing was wrong. We do not do this. And also the other common mistakes that we already established for compound interest and the other present value for compound interest also apply to this, of course. So we're trying to go off the beaten track here and go for something a little more extravagant. So input our variables. So the R amount, we do not know that. That is what we're trying to find. How much he wants every year. How much money would he get every year? Is equal to 1 minus 1 plus I is 0.045 because 4.5 interest rate per year annually, compounded annually, and he's also doing it per year. To the power of negative 4. Let's assume that he has 4 years of university. Over 0.045 interest rate. So I'm going to put that into my calculator here. You guys can follow along. So we have 1.045 to the power of negative 4. It's approximately 0.83. Subtract that from 1 and divide by 0.045. And I get an approximate value. Again, it's an approximation. So we have $6,417.29, which equals an approximate value of 3.59 R. So if we divide both sides by 3.59, we get a value of, let me just put that in, we get a value of $1,700.88. So that is the amount he would be able to withdraw each year using the money he made during high school to pay for his university. Let's check that with our answer. And look, we are correct. So that is all for the present value of an ordinary annuity, and join us next time again for a new concept on Math Toolbox.